Caroline is based at Sydney University, and she's going to present on galaxy interactions, which is really cool, I think. I always like to tell my physics students that, you know, if I could fast forward time and just sort of watch galaxies collide, like looking at Andromeda, that'd be something really cool to sort of visualize. But hopefully we can hear some of that sort of stories from Caroline. So Caroline, whenever you're ready, feel free to take over the screen, and thank you very much for joining us.
Does this work? Are people seeing my screen?
Yes, that's perfect. Yeah, thank you so much.
Fantastic. I might share video. Okay, well, hopefully people can see and hear me fine. So thank you for the introduction. I'm normally based at Sydney Uni, but right now in the comfort of my home, a beach in Hawaii, as you can see in the background. So today I'm going to talk about how galaxies acquire their shapes and the role of spin in shaping galaxies. So we will be talking about interactions, but not only about interactions. Let's see, I think, click, okay, perfect. So it's good that we heard a little bit about, I got to hear at least the end of Lisa's presentation and at least our answers to your questions. But the first thing that was given to me when I started my PhD in Melbourne some years back now was an article that my advisor had just published in just a magazine. It said, the title was, "So you want to be a professional astronomer?" Exclamation mark. It started with exotic workplace locales, amazing discoveries and fame, but probably not fortune, await those who persevere on the path leading to a career as a professional astronomer, by Duncan Forbes, my supervisor. The first paragraph said, wanted, astronomer, must be willing to work occasional nights on the top of a mountain in an exotic location, like the one behind me. A sense of adventure and nomadic lifestyle is a plus. Flexible hours and casual dress code compensate for uncertain long-term career prospects and average pay. I'm really not selling this, am I? The opportunity for real scientific discovery awaits the right candidate. Apply now. And I have to say, that's been very true for me, although, I keep forgetting I need to click. Okay, on a normal day, this is kind of what I do. So I spend a lot of time coding and working at my desk. So it's mostly an office job. But the more I progress in my career, the more I interact with students, and there's a bit of lecturing involved as well. So that's mainly what a day in the life of an astronomer looks like. It has taken me to all sorts of cool places. This is just I think it's all of them, if I remember correctly, the various telescopes and observatories that I've observed at. Notice that the map is upside down. I've decided to pick the map that puts Australia up the top for once. But you can see that it has taken me around the world a fair bit, this astronomy. Very exotic locales, as you can see. When you observe, for example, in Hawaii, you can be here at sunset and then the next afternoon having a dip in the ocean. Okay, well, let's talk about what I actually came here to talk about. So I'm going to recap some of the things that you've already heard about today, I think, just to put them into context so that it fits into the whole story of what I'm going to talk about. So I'm going to just rehash a little bit the electromagnetic spectrum of light to start with. You've seen something similar, I think, from Chris. Basically, light is a whole spectrum. Our eyes only see a very small part of it. This tiny area here, I hope you can see my mouse, where the rainbow is, that's the visible light. That's all that our eyes can see. But the electromagnetic spectrum of light extends far beyond that to much longer wavelengths with the infrared and the radio, and to much shorter wavelengths with the UV, the X-rays, so the more energetic wavelengths. Higher energy to the right, lower energy to the left. And obviously our own bodies glow in the infrared, so that's why night infrared cameras work to see people. Okay, this is a spectrum of the sun. As you can see here, the peak of the spectrum, this is wavelength on the x-axis, and just basically how strong the spectrum where the light is at that wavelength. And you can see that it peaks right around where, oops, not what I wanted to do. Right around where our eyes, so where that rainbow is, which is the visible wavelengths are. And that's basically our eyes have adapted over, evolutionary, throughout evolution to actually be tweaked to the same wavelength that the sun peaks at. If the sun was a bit cooler, it'd be further to the right. If it was a bit hotter, it would be further to the left. You can see here that the sun still has UV light, and thankfully our atmosphere filters a whole lot of it, but not all of it. And then quite a bit of heat, thankfully, because that keeps us warm and cozy, and that's why life forms like us humans are very happy here on the planet Earth. The very energetic wavelengths, so very short wavelengths, like the UV, for example, and X-rays, are so high energy that they can in fact knock out some of the atoms out of your DNA, like this, like is shown here. And that's basically what happens, for example, if you go out in the sun and then you don't wear sun cream. And so that's why, no need to worry about it. Let's just make sure we live in Australia that we wear our sun cream. That's very important, because those UV rays that are not filtered by the atmosphere, they are very, very strong. Okay, now let's move on to a discussion about astronomical images. This is important to understand the shape of galaxies. Okay, things that we know from images. Basically, I'm going to focus as well on how galaxies form and evolve. So we're going to look back in time in this slide. And if we look 8 billion years ago, this is the galaxies that are here on the left. So these are much younger versions of the galaxies that we see today. And what you see is these quite clumpy galaxies. They're very fluffy. They seem to have what we astronomers call gas, which is all that fuzz and fluff around here. And they don't seem to be very well ordered or organized. They're much more messy. Galaxies that we see today, this is a bunch of examples. There's an edge-on disk galaxy. You can see a little bit of dust there still. You could think as well of, these are all one type of galaxy. They're kind of older ones. We do have like the grand design spirals like the Milky Way, for example. But they're much more organized. Even our own Milky Way, which has a lot of gas, looks nothing like these galaxies at higher redshift. It's very organized, a beautiful disk with long spiral arms, a grand design spiral. And so galaxies have changed a lot in time. They started more chaotic, and today they're much more organized. Also, when you look at galaxies, so if you looked at the same galaxy, but you looked at different wavelengths, the galaxy looks very different as you focus on different parts of galaxies. So for example, if you looked in the ultraviolet, you mainly probe the very, very young, very, very hot stars that shine mostly in the ultraviolet. And then you move your way to the optical wavelengths, and then you're more dominated by the older sort of populations. And a lot of the stars are obscured by dust because the dust is very opaque to light. So you can see here in those images that there isn't very much here where there's the dust, for example, in the spiral arms, it's quite dark. But as you move to the infrared, the dust shines in the infrared, and so it's easier to peer there. Okay, so basically astronomers from as soon as they discovered that galaxies were actually not part of our Milky Way, but their own little island universes, if you like, started classifying them a little bit like you would classify animals in a taxonomic sense, where you would put them into families. So you put dogs with wolves and so forth. So we like to do the same here with galaxies, and we like to find an order, if you like. So the earliest or the most common or popular such scheme is the Hubble galaxy classification scheme. And it basically often is referred to as the tuning fork because it has a tuning fork shape, especially if you ignore the irregulars here, which have just been plumped there. They don't really belong in the middle. And so you've got a sort of a gradient in visual properties of galaxies going from here on the left-hand side, galaxies that we call ellipticals, and moving on to more flattened elliptical galaxies, which are labeled here as E, and the flatter, the higher the number. And then we move on to the lenticular galaxies. So the S-zeros is another term you might hear from those. They don't show spiral arms. That's kind of the key thing that differentiates them from spirals, but they have a disk. So they are quite flattened systems. They can also have a bar. So what differentiates the two forks of the tuning fork in this case is that the lower fork has bars. So if you look in the very center of these galaxies, there's a shape, a sort of a flattened nucleus, which is called a bar. So this long stretch here, that's called the bar. So all the galaxies at the bottom have bars, and the ones at the top don't have a bar. That's what differentiates the two branches. And then as you have more and more spiral arms, and they're more and more twirled together, you move from a spiral A to B to C. And obviously these irregular galaxies don't really fit that. They're usually either just like very highly star forming, very messy new things, so they haven't quite settled. They look more like the things that we see at high redshift, I suppose. And then you have the also like the train wrecks from mergers. So they can look like this a little bit. So the irregular galaxies don't really fit that pattern. Okay. I noticed, I'll point out as well that there are a gradient in color in that tuning fork as well, going from redder systems to bluer systems. And I guess I have a question on the slide, which you may have been pondering, and I'm about to answer it. But let's see, have your own mental answer and then see if you got it right. So what do you think the colors might mean? Okay, so there's a partial answer. Actually, that's probably the bulk of the answer. Is basically the age of the star. So if we have a look here at the stellar nursery, the plot in the middle, or the image in the middle, if you look here, the stars that you can see in that picture are all blue. And they're surrounded by, it's a stellar nursery, so it's surrounded by this gas, which is essentially the fuel for star formation. So there's a lot of brand new stars in there, and stars that are currently forming. And when they are new and the gas dissipates from around them, you can see that they're very, very blue. So young stars, baby stars, are very blue. And then on the flip side of that, on this side here, I'm showing a globular cluster, or probably what we think is the remnant of the core of a small galaxy. And you can look there, and the vast majority of the stars in there are really red, okay? It's a hue of red. I agree, it's not bright red. It's probably reddish, if you like. But those stars are all very, very old. The globular clusters around our own Milky Way all tend to be around almost the age of the universe. So that's what an old stellar population would look like. So the first part of the answer is age. The second part of the answer is metals. You would have seen, I suspect Lisa would have discussed this with you, but I'm an astronomer, and I know that you would have all seen this periodic table of elements in school, but let me simplify it for you. This is what astronomers think about metals. So we think almost everything is hydrogen. There was some helium produced in the Big Bang and also in the inside stars. And then we just call everything else metals. And then we have metals that are before iron, because you can fuse things all the way up to iron. So iron is an important one, okay, right here, but you can't fuse past iron. So once you get there, there's no fusion that can keep your star going. And so that's why it's called a star killer. Once you get to iron and you've transformed everything into iron, the whole thing collapses and explodes as a supernova. And so in that explosion, then are all the other elements created. That's what here is called supernova output. Okay, and so how does the color of a galaxy change as a function of the metals that are in it? So remember, for me, metals is everything above helium. So if we have something, we call it metallicity here, metal rich, metal poor on the y-axis. So, and then on the horizontal axis, I've put the color going from blue to red. And all the dots that are there, all the points, are globular clusters from different studies. And as we saw before, all the globular clusters are old. Okay, so basically the main thing that changes between them here is their metallicity. How much metals, how many higher mass atoms are present in the stars, in those globular clusters. And you can see quite clearly here that if you keep the age constant for old things, you will see that metal poor objects will be blue and metal rich objects will be red. So by and large, what determines the colors of galaxies is first of all their age and then their metallicity. Okay. Galaxies also, like their change the way that they behave or they evolve depending on what company they keep. In the same way that if we live in the city downtown versus if we live in the bush or if we live in the suburbs, we might do different activities on the weekend because there are different things to do that are available. It's the same for galaxies. They behave differently depending on where, one, they are born and also where they are raised or where they grow up. And so you can see here, just by looking at this picture, this is basically two clusters of galaxies that are about to merge. And you can see the very centers of them are these very big behemoth galaxies. These are called brightest cluster galaxies because they're huge and they have very strong gravity, lots of dark matter, and they attract everything around them. And they're about to collide as well. Those two clusters are about to collide together. But if you look at the galaxies that are really near the central galaxies, you will see that their color by and large is red. And have a look at their shape as well. Okay, just their shape on the image, how they look. And then if you move away from that, you start seeing little flattened things and also bluer things. More flattened and more bluer the further away from the centers. Okay, so it seems like depending on where you are and where you live in the universe, that changes significantly, well, your color, so the age of your stars potentially, and also your shape. So that's an important clue. Okay, this is not new. This has been known for quite some time. And I lost my reference here. Okay. So this is quite an old paper. You can see that when you live in the suburbs here versus in the CBD, so to speak, for high, if you have a really high density of other galaxies around you, there tends to be much fewer spiral galaxies and much more elliptical galaxies. And the reverse is true in the suburbs, as I was pointing out in the image. Okay, so this is what we learn just by looking at images. We can learn an awful lot about just galaxies and how they form just by looking at images. But let's throw in spectroscopy because that is very exciting. There's way more in there. I'm not sure how much spectroscopy you've seen today. I assume quite a bit. But let's just have a quick recap and see what we're looking at here. I imagine a distant photon coming from, one of those galaxies a couple billion years ago, traveling through space, coming to Siding Springs, New South Wales, onto the Anglo-Australian telescope, bouncing off the mirror. It goes through a fiber optic all the way down to the basement where there is an instrument called AA omega, which is a spectrograph. A spectrograph is essentially a bunch of optics, which we're going to go through now. So you can see the light rays now are bouncing off a mirror first, and it's going through a bunch of lenses, which will essentially change the paths of the light so it can be aligned. Now the light's getting split by a dichroic or a prism, and it's all getting aligned so that the colors all end up at the same place on my detector, so it's easy for an astronomer to then interpret. So that's what all these bits of optics are for. So once it hits the detector, it's very clear, purple on the left and red on the right. And this is what actually an image from the telescope would look like. And these are two spectra that would come out of that. And I can tell just looking at these spectra what type of galaxies they are. So the spiral at the top and the elliptical at the bottom. I'll go back on that to explain how I knew that just in a minute. Okay, so here they are, my spectra again. I've got a spiral galaxy here at the top. and an elliptical galaxy at the bottom. Let's look at the spiral galaxy at first. These are spectra just for the very center. Hopefully you can see my red circles here. There's a very center nucleus of those galaxies. And so what I see here is essentially for a galaxy like this one, these booming lines here in the spectra, they stick out. See, they're labeled oxygen 2, so doubly ionized oxygen, H beta, hydrogen beta. These are all atomic transitions, and they have these very narrow, sharp emission lines around these atomic transitions. And basically, this, what I'm looking at there that is creating those lines are the things that Lisa was talking about. These are the emission lines that show, that are from the gas that surrounds those young stars. So when there's a really hot young star that's surrounded by gas, it can ionize that gas, and then it will then re-emit the photons from those stars into an emission line, and that's what it looks like. So by just looking at this spectrum, I know immediately this is a star-forming galaxy. It's got very bright young stars and lots of gas, okay? And then looking at this spectrum now, I don't see those very bright emission lines, but I see a bunch of other features. See here, there are two very close together. That's calcium H and K. I've got a sodium line here. So there's an awful lot of information here about the different types of elements that are present. And these lines arise from the atmospheres around stars. So very much here, what I'm probing is not the gas like I was probing up here with the emission lines, but the stars themselves. Okay, so an older population, and then just the stars because there's no more new stars born. If you squint a little bit in this spectrum as well, you can see some of the features even in the absorption. So this is the continuum here. Okay. But this is just one spectrum, right? We don't know what's happening outside in the outskirts here, on the outside of these galaxies. We really cannot tell. So this is where integral field spectroscopy comes in. An integral field spectrograph is basically, instead of having one spectrum on the object, a single fiber, for example, I might have a bundle of fibers illustrated here where I pack them tightly and then try and cover the whole galaxy so I can get an image, if you like, in 3 dimensions. So what you then get out of this is a cube for each galaxy. So by a cube, what I mean is basically what's illustrated here. You have the image, and for each pixel on the image, we call them spexel, I get a whole spectrum. So all the information that I was showing you before that I could see in my spectra, I have it for every single pixel or spexel. Or you could see it as for every wavelength slice, I have an image, or yeah, an image of my galaxy. So that's incredibly rich and dense information. And now you can even multiplex that. You can have more than one integral field spectrograph on a single instrument. And this is what the SAMI instrument is. So here I'm just showing a video. This is my colleague Amanda. She's about to prepare for observations for the SAMI survey. SAMI survey observed 3,000 galaxies, looking at 12 galaxies at a time. And so you can see here in gray, so the probes that Amanda's about to pick, that's an integral field spectrograph. It's that small. And she's putting into a hole that has been drilled into a metal plate. And that hole, once we point the telescope up at the sky, is exactly aligned with one of our targets. So that once we go on sky, we know that we're going to get light from that galaxy. We have to change that plate 2 or 3 times a night. Once or twice a night. We set it up at the beginning, then we change it once or twice as we observe throughout the night. So we observe, anything between 24 to 36 galaxies per night when the survey was in full swing. There she is, removing the plate, putting a new plate, and off she goes again. So she starts with those orange cables. These were to observe the sky, to calibrate, so that we can remove the artifacts from the sky. So here's an example, for example, of like a galaxy that SAMI might have been looking at. This is what SAMI data will look like. And this is what it looks like on the detector. This video is already quite old, so already the telescope is older than that. But it's amazing that with this kind of instrumentation, it's really doing some quite cutting edge science. That's all very exciting. Something else that we get from spectra is what astronomers call the redshift. This is very similar to the Doppler shift, which you might have seen in your science class, for sound. So when you have, for example, an ambulance coming towards you, the sound waves are compressed and the pitch sounds higher. But when it goes away from you, the sound waves are stretched and suddenly the pitch is lower. Okay, and it's the same for light. Okay, so if something is moving away from us, all those emission and absorption lines I was showing you in the spectra, all of them get shifted to the red. If something is moving towards you, all of these lines get shifted to the blue. And that means that we can measure the speed towards and away from us when we look at the galaxy. So every time we take a spectrum, we also get lots of velocity information for that object. So if I have a data cube, that means that I can measure the speed that the stars are moving at for every point in my image. So if I have an image here, this is just an example, and then I have my velocity map here at the bottom, I can see that all of these points here are moving more towards us, and all the points here are moving more away from us. So I can infer that this galaxy is rotating, right? This is a measure of the organized motions in that galaxy. Also, what we get with those spectra is a measure of the random motion. So how many of the orbits don't fit with the bulk motion, but just kind of do their own thing. And that's what this other map is showing. I'm not really going to discuss this velocity dispersion map, but I just wanted to let you know since I'm showing it. Okay, so is it all galaxies that rotate? And does it matter that galaxies rotate? And how does that change the way that they look like? Well, the other thing as well, I'll leave that question hanging and get back to it. But another thing that's really interesting here, because we were showing before the morphology density relation, where we had galaxies, more elliptical galaxies in the center of clusters than in the outskirts, and vice versa for the spirals. Well, what we find as well is that this is also true in the way that galaxies spin. Galaxies that spin fast tend to live in the outskirts of clusters, and galaxies that spin very slowly really prefer the dense areas of clusters. So here on this plot, we are showing the contours of the density contours of this galaxy cluster. And in red are the galaxies that rotate slow, and in blue are the galaxies that rotate fast. There's much more galaxies that rotate fast than there are that rotate slow, but if you rotate slow, you're more likely to be in one of those dense knots. Or as one of my colleagues, Professor Cerebroff, likes to say, big galaxies don't dance in crowds. See, in astronomy, we really like to anthropomorphize our galaxies. We like to give them human traits. Okay, so what does it all mean? And what can we learn? And what have simulations shown us that all of these things that we observe in the spectra, in the images, might mean for our galaxies? So this is a bit of a galaxy formation crash course. I hope you'll bear with me. By the end of this, you'll all be experts, hopefully. Okay, so the simulations tell us that the appearance, the shape, and the dynamics of galaxies trace the way that they have formed. So if you imagine a cloud of gas, because it's got some gravity, it'll start collapsing on itself. And there will be one direction which will be shorter than the other, and that one will collapse first because for the same reason that my figure skater right now, once her arms are out, she's not rotating so fast, pulls her arms in, starts spinning faster. Okay, so what will happen as the cloud collapses is it will start spinning around its shorter axis, and that will keep that longer axis from collapsing as well. So those rotating motions will actually give it a stable, make it stable into more like a disk. As gas collapses as well and condenses, it can start forming stars. And what you end up is a spinning disk. If there's still gas, it might still be star forming. If there's no more gas, it might still stay as a disk, but just be a bunch of stars in a disk pattern. Okay, so now let's throw some randomness in here, okay? What if I have already a galaxy like this red one here, which is just a red ball, and I start adding gas to it, just gas from, you know, the outside, somewhere else in the universe. Some gas comes in and that happens. And then as the gas falls in, it starts forming stars. And because, as I showed before, when you have collapsing gas cloud, it tends to collapse into a disk because it starts then spinning. And so you end up with a rejuvenated disk, if you like. So you had a sort of ball of stars, and now you had new gas, and it created a new disk. What you could have as well, you might have two galaxies that are, let's say, elliptical galaxies, and they merge together. And as they merge, then their stars get mixed up, and that basically puffs up the system. So you end up with something that's much more round than what you began with. And there's no gas to rebuild the disk to make it more flat again. So it just stays more poofed up. What if, for example, you had two galaxies that had gas in them, that had these gas disks, and you merge them? You'll end up with something in between. Okay, you might reform a disk if there was enough gas, or you just might end up with something that's a little bit rounder than the initial disks because of the mixed orbits, but also flatter than if you had merged two things that didn't have any gas. Now, the best way to create the roundest possible galaxy is to merge a whole bunch of things together. So if you merge two things, then you remerge those together and so forth, or you just had a whole bunch of little things to something, that's when you end up with the roundest possible galaxy. That's what simulations tell us. Okay, but if there is gas in that process, so if I'm, for example, the central galaxy in the center of a group, and all of these group galaxies are falling in, I'll end up with something that's in between. Okay, not quite the extreme that we had before we had a spherical galaxy. Okay, so let's talk about galaxy shapes, and let's test some of these simulations. I'm going to use the SAMI survey to try and see whether I can measure shape, and if I can tell the difference if galaxies are spinning faster or slower in their shape, and see if I can make sense of that in the grand scheme of galaxy formation. So first of all, let me define what I mean by shape. Physicists love to talk about spherical cows, okay? That's just a joke that we make to basically say when we make working assumptions, you know, assume a frictionless plane, things like that. It doesn't exist in real life, but okay, it's a working assumption. So now in this case, a spherical cow is a bit too simple for me. I think I need a spheroidal cow. So we're going to assume a spheroidal cow, or I should say, we'll assume that our galaxies can be explained as spheroidals. Okay, if you have a spheroid, it can have three main or basic shapes. It can be prolate, well, of course it could be spherical, okay, which would be a sphere. It could be prolate, which is more like an egg shape or a football shape. You could have an oblate system, which is like a squashed ball, or a disc would be oblate in shape. And then triaxial, I call it like potato shape, where there isn't like a clear symmetry in the shape. Okay, before I move on, I think I can hear through the waves that someone is saying, well, don't we know the shape of galaxies? Isn't that like a boring question to ask? Actually, we don't. It's one of the oldest questions that astronomers have been asking, because unfortunately for astronomers, we only have the one universe, and we don't see it evolves so slowly that we don't really see a change, or some things change, to be fair. But for galaxies, in terms of how they look on the sky, they don't change very much over a human lifetime or over all of human history. So we cannot sort of fly around or see how they look like. We don't see the form evolve or revolve, so we cannot tell really what shape they have. And so here I have an analogy with shadow puppets, where I have two very differently shaped galaxies, that project exactly the same on the plane of the sky. So you can't tell them apart by just looking at them with your images. But if you had a large enough sample and you assume that they're all randomly placed in the sky, then maybe you have some hope for a population of saying how on average that population is shaped. Okay? If you have just imaging and then you look at how the galaxies would look on the sky, so how elliptical, are they very round, circular on the sky, or are they very elliptical on the sky? Depending on their original shape, their 3D shape, and how that distribution changes depending on the shape. This is what you see here. If I have just imaging and I just look at how the apparent ellipticity looks like on these images, and I have something that is quite flat, like this purple disk here, I'll get a range of observed ellipticities depending on how I look at it. Whereas if I have a very spherical system, then I end up with almost, well, I always measure a spherical or a circular image. Okay. I have another observable here that I can only get through spectroscopy, getting those mapped from the integral field spectrographs that I was showing you before. It's called the kinematic misalignment. And if I include spectroscopy, I also get a little bit of leverage on trying to understand how flat the galaxies are, but not very much, okay? So basically in this case, imaging is very, very good at telling me one dimension, how flat a disk would be if I had an oblate spheroid, for example, okay? So if I look at something edge on, how flat is it? Imaging is really good for giving me that. But imaging is absolutely useless to tell me basically how circular the disk is of my galaxy. If I look at a galaxy face on and I stare at the disk, I would not be able to tell you if it's squashed or not. I would not be able to tell the difference between it being squashed or just being at an angle. Okay, so imaging is useless for doing that. But spectroscopy gives me that third dimension. Okay, so you can see here where I've moved the extremes of how squashed my disk is. And so depending on how squashed it is, going from purple where it's basically circular to red where it's squashed, I can see a very significant difference in that parameter in spectroscopy. So using those tools, I'm able to invert those distributions that we see in the galaxies and actually understand their shape. Okay, so that's what I did. These are SAMI galaxies. Well, okay, these are parameters measured on SAMI galaxies. So we've got the projected ellipticity, which we get from the imaging, and the spin here, which we get from the dynamics, okay, from the spectroscopy. And I've put each point here basically shows me where an individual galaxy would be. Okay, so we go from the roundest looking ones on the images to the flattest looking ones on the right. And then from things that rotate very little, very small spin top here, to things that rotate very fast with a very large spin top. So a galaxy that is up here is quite flattened and rotating fast, and a galaxy that's down here doesn't rotate very much and is quite round. Oh, sorry. So I've divided my SAMI sample, so the whole of the SAMI survey, into a bunch of samples. First of all, I did 4 SAMI spin samples, which you can see here in the colors, where I've just made straight cuts in spin. Okay, so there's a red sample, which is very low rotation, and a blue sample, which has the highest rotation. And I've also divided them. Astronomers, for some reason, like to do fast and slow rotators, and the dividing line for those is the red line. Okay, so you've got light gray points. These are my slow rotators, and the dark black points, the black field points, sorry, are my fast rotators. So those are the samples that I looked at in the SAMI survey. Okay, so I'm just gonna go through my conclusions, and hopefully you'll see that actually I think the simulations did pretty well there. So we're looking at here, basically that's the typical slow rotator galaxy, the typical R1, which was my lowest, so the red, so the colors correspond, right? So here I had red here, orange, green, and blue, red, orange, green, and blue. So from lowest to highest spin, okay? And so you can see, if you look at this, if you're a slow rotator, this is your shape. You're still oblate. Okay, it's not, I wouldn't call that a disk, but it's basically like a squashed ball, if you like. That's a typical, what a typical slow rotator galaxy would look like. And here's a typical galaxy for the lowest rotator, and then moving up to the fastest rotators where you have really quite a thin disk. Okay, so what you can see from here is that one, rotation, so the higher rotation, leads to flatter galaxies and rounder disks. Two, most galaxies, almost all of them, are shaped like sea urchins. So almost all the galaxies, whether they rotate faster or not, are a little bit squashed spheres. Okay, and then galaxies that rotate slower, they're more likely to be potato-shaped. So you can have potato-shaped galaxies. If you are potato-shaped, you're very likely to be a slow, a slow rotator, or the slowest rotation galaxies. I would say this is a bit potato-like to me. Triaxial is the right word. Okay, so galaxies that rotate fast and galaxies that rotate slow likely form differently. That is what, I mean, they look vastly different, but that is also what the simulations tell us. Now, using the simulations to interpret this, we conclude, and also comparing with the content of the galaxies, their color, if there's gas and so forth, we find that the fastest rotating galaxies, they tend to be the spiral galaxies. They have lots of gas that we can still see. They still have star formation. So they're more likely to have formed in a process like this, where there was a lot of gas involved and not many mergers. On the flip side, if you have something that rotates very little, if you want to stop the rotation from happening, you cannot have new stars and new gas coming in. So it's more one of those scenarios here where you don't have gas. And then the things in the middle are probably the middle scenario. So that was kind of the conclusion or the speculation of this study. Okay, so I hope now you feel like you know a whole lot more about galaxy formation and evolution. I hope you found this interesting. I've left here a little quiz. You guys can ask me those questions, or you can have a look at them later at your own time, or see if you can test your own knowledge, see if you were paying attention. Leave that up to you. Happy to take any and all questions at this point.
Hello, Carolyn. I think there is one question in the question and answer section.
Yeah. Okay. Do you know what happens at the extreme ends of the electromagnetic spectrum? Is there an absolute maximum gamma and minimum radio? Oh, that's a good question. Yeah, no, I don't know. Yeah, I think there's a question about whether it goes on infinitely on either side. And I don't really know the answer. I suppose one way to kind of think about it, and my hunch would be that no, it doesn't go infinitely, is because, well, at some point, so the wavelength of the photons is related to their energy. And so at some point, you just don't have energy anymore. And so there cannot be a photon of negative energy, I don't think. So I think there must be a lower end energetically. Higher end, yeah, there must be, I mean, there's only so much energy one can output. And so there must be a maximum as well, but I don't know exactly where those maximums and minimums are, but that would be my shorthand answer to that one.
Caroline, I really liked how you tied that SEMI data in. It's really cool to see, you know, someone like Amanda in the telescope putting in that plate in, and then getting that data, and then analyzing that data, like going from, you know, literally the focal plane of the telescope to the computer screen. Sort of.
Yeah.
Any other questions online? I'm just going to check the question and answer. There's only just that one there. So I'll ask a question if I may, Caroline. Are you primarily based at Sydney University, in the sense that that's your home university where you operate out of still?
Yeah, absolutely. Yeah.
And do you still travel to Siding Spring Observatory to do things up there?
So at the moment, the SAMI survey is over. So we have finished our observing campaign. We've observed just a little over 3,000 galaxies. So when the survey was in full swing, yeah, I did go. I went there maybe 2-4 weeks a year, I would say, no more. Nowadays, I observe actually similar to the SAMI survey, but galaxies at higher redshift. So looking at galaxies about 4 billion years ago. And that's about as far as you can hope to get with an integral field spectrograph, where you can get all the information that SAMI is getting, for example. So we're trying to really push that boundary with an instrument that is on the European Southern Observatory in Chile. So on the Paranal Observatory, and it's called MUSE. It's quite a behemoth of an instrument. It's huge. It's taller than me, wider than 10 men. It's huge. And it's got all these like cables sticking out of it. It's really cool. But for that one, I don't need to go to Chile. So someone else, I send them my observations, which I prepare, and someone else observes them for me, and I just get an email whenever the data's in. So yeah, I don't get to go to observatories quite as much lately. I see there's a question. When galaxies compress and form, is there a limit to how much they can compress? That's a good question. That's an excellent question. There's so many layers to this. Okay, what happens when a galaxy forms? It forms a disk. When you form stars, the stars actually inject energy back into the gas, which puffs it up. It heats it up. So that means that there's kind of a feedback process happening, such that you could never have an infinitely thin disk, if you like. And so a lot of the simulations were actually getting it wrong, completely wrong, because their prescription for star formation was actually putting it too much heat, making it too puffed up. And that was basically because we didn't have refined enough, if you like, pixel or particles in the simulation. So we couldn't get very, very thin disks. But we observed them. We observed very, very thin disks. So despite stars, when they form, ejecting a lot of energy, it seems like galaxies are able to produce very thin disks. Yeah, so I hope that answers it.
Well, thank you very much for your presentation, Carolyn. Really enjoyed it, and taking time out of your day to talk to, I think we've got over 400 students online, which is pretty cool.
That is cool.
And yeah, seeing where astronomy has taken you, and I really like that slide at the start, you know, come and be an astronomer, work late nights on a mountain, potentially in the cold.
Definitely in the cold.
Okay, well, thank you, Carolyn. I'm going to hand back to Delise in Canberra now.
All right, thank you. I'll stop sharing.